We experience gravity intuitively as a mechanical pulling force. It feels like an invisible tether anchoring our feet to the ground and dragging massive celestial bodies toward one another across the void of space. Isaac Newton formalized this intuition with the inverse square law. He provided the mathematics to predict exactly how objects attract each other in direct proportion to their mass and in inverse proportion to the distance between them. Measured, yet Newton himself recognized a severe limitation in his own model. He coined the term action at a distance to describe how gravity operates, admitting he lacked any physical mechanism to explain how a force transmits through completely empty space. This lack of a propagation mechanism sat unresolved for centuries. The equations worked for engineering and navigation, so the missing physical cause was largely ignored. Describing the mathematical effect of a force is not the same as identifying its physical cause. We knew exactly where planets would move, but we did not know why. This historical astronomical diagram maps the comparative sizes and orbits of the planets in our solar system. Testing Newtonian mechanics against strict observational data at this macroscopic scale reveals a fatal flaw in the classical model. We look to Mercury. Astronomers observed its perihelion shifts slightly with each orbit, tracing a steady precession. This measured variance did not match Newton's equations, an undeniable error margin the classical pulling force could not predict. This discrepancy was too large to write off as an observational error. It proved that the theory of classical gravity broke down entirely at the macroscopic scale. Albert Einstein resolved the Mercury anomaly by completely discarding the concept of an attractive pulling force. To predict Mercury's true path, physics had to abandon the invisible tether and adopt an entirely new geometric reality. Under general relativity, gravity is defined strictly as the manifestation of a curved pseudo-Riemannian manifold. It is a property of the geometry of space and time. Objects traveling through this space follow a geodesic, the straightest possible path through a curved manifold. If you draw two parallel lines pointing north from a sphere's equator, parallel transport dictates they will inevitably converge and intersect at the pole. Neither line exerted an attractive force on the other. No lateral pressure pushed them together. Their collision was a purely geometric inevitability. Mass does not actually pull on other mass. A massive object simply alters the geometric routing of the space surrounding it, creating the illusion of an attractive force. This curvature is not isolated to 3 spatial dimensions. It occurs across a 4-dimensional spacetime manifold, and the time dimension is responsible for the effect we experience as falling. Introducing a mass creates a gradient of time dilation. Time flows measurably slower closer to a massive body. When an object travels straight along the time axis and passes through this gradient, its straight world line naturally bends inward through the spatial axis. To a localized observer, this deflection through the time gradient registers physically as spatial acceleration. The downward acceleration we feel standing on Earth is simply our world line continually bending into a gradient of slower time. Space-time geometry accurately maps the routing of objects, but it leaves a crucial question unanswered. What physical mechanism generates that curvature in the first place? Physics looks to emergent phenomena for the answer. A single atom lacks temperature or elasticity. Those properties emerge entirely from the statistical mechanics of millions of interacting particles. Physicist Eric Verlinde proposed a model of holographic entropic gravity, arguing that gravity operates as exactly this kind of emergent statistical effect. In this framework, quantum bits are distributed on a holographic screen surrounding a mass. As a test particle approaches, changes in this information create thermodynamic pressure. We can calculate this. The entropic force equation, temperature times the entropy gradient, translates cleanly into classical Newtonian mechanics. Ultimately, what registers to our senses as a gravitational pull is the universe mathematically maximizing the entropy of quantum information. A related theoretical framework grounds this process in the quantum vacuum, presenting gravity as a macroscopic version of the Casimir effect. The vacuum of space is not empty. It contains a baseline ground state energy density that acts as the transmitting medium for gravitational interaction. This theoretical approach deconstructs Newton's gravitational constant. The math indicates that the constant is not a fixed universal law, but an environmental variable. The equation calculates the gravitational constant entirely through the total mass energy and the total size of the observable universe. If the observable universe contained a different total mass or possessed a different radius, the localized strength of gravity on Earth would proportionally change. Gravity is merely an illusion of force. It is the geometric routing of an object through time, ultimately born from the macroscopic statistics of quantum vacuum energy and information entropy.